Now you sit there and you look at me and you say, Feynman, the apple falls from the tree because gravity pulls on it. You got this idea in your head of a force, like a little invisible string tied to the apple, yanking it down toward the center of the earth. It's a very comfortable idea. It's what Newton told us, and Newton was a giant, don't get me wrong, but if we want to really understand the machinery of the world, we have to be willing to look at it differently. We have to be willing to admit that our common sense is often just a collection of prejudices we picked up before we were 18. When we talk about a force in the old sense, we're thinking about an interaction. I push you, you feel a poke. But gravity is a much more subtle and beautiful thing than a simple poke. Einstein came along and realized something that sounds like science fiction, but it's the way the world actually works. Gravity isn't a force acting through space, it's the behavior of space itself. Imagine you have a big, flat sheet of rubber, stretched out tight. Now, you take a heavy lead ball, let's call that the sun, and you plop it right in the middle. What happens? Now, if you take a little marble, the earth, and you try to roll it across that sheet, it isn't going to go in a straight line anymore. It's going to follow the curve. It's going to roll around the big ball. Now, is there a string pulling that marble? Is there a force reaching out and grabbing it? No, the marble is just trying to go in a straight line, but the ground underneath it is curved. This is the key. Space and time aren't just a stage where the actors, the atoms, and the light run around. The stage itself is part of the play. It's flexible. When you have something with mass, it tells the space around it how to curve, and then that space tells the mass how to move. It's a beautiful circular dance. Why do we call it a force? Because it feels like one. When you're standing on the ground, you feel heavy, your feet hurt. You think gravity is pulling you down. But let's do a little thought experiment. And I love these because they don't cost the university any money for equipment. Imagine you're in an elevator and the cable breaks. Ignoring the messy ending for a moment, while you're falling, what do you feel? You feel weightless. If you let go of your keys, they just float there next to you. Are the keys falling? Yes. Are you falling? Yes. But relative to each other, there's no force between you. You are both simply following the natural straight path through curved space-time. Einstein called this the equivalence principle. He realized that being in a state of free fall is physically the same as being out in deep space, where there's no gravity at all. If you can't tell the difference between no gravity and falling in gravity, then gravity isn't a thing that's being done to you. It's just the geometry you're moving through. Think about two people standing on the equator of the Earth, a few miles apart. They both start walking exactly due north. They're walking perfectly straight lines, not turning left, not turning right. As they get closer to the North Pole, they notice something strange. They're getting closer to each other. They didn't try to move toward each other. There was no magnetic attraction pulling them together. They just followed the straightest possible lines on a curved surface, and those lines happened to converge. To them, it might look like a mysterious force was drawing them together, but we, looking from the outside, see it's just the shape of the Earth. That's gravity. We are moving through time. And as we move through time, the curvature of space-time nudges our path. We think we're being pulled down, but down is just the direction of the curvature toward the center of the mass. Now people ask, how does it curve? Well, it's the energy and the momentum that do it. The math is a bit hairy, you need 10 equations to describe it properly, but the physical idea is simple. Matter tells space how to curve, and space tells matter how to move. It's a feedback loop, and it's not just space, it's time too. This is the part that really messes with your head. Gravity slows down time. If you have a very accurate clock, and you put it on the floor, and you have another one, and you put it on the bookshelf, the one on the floor will tick slightly slower. Why? Because it's deeper in the gravity well. The curvature affects the very rhythm of existence. You might say, Feynman, this is all very clever, but if it's just geometry, why does it hurt when I fall off a ladder? That's a fair question. The force you feel isn't gravity, it's the ladder, or rather, it's the ground. The ground is what's pushing up on your feet, preventing you from following your natural path through curved space-time. You want to go along the curve, but the atoms in the floor are in the way. They're pushing you up with electromagnetic forces. So, the force you feel is actually the floor pushing you out of your natural gravitational motion. You spend your whole life being accelerated upward by the ground, just to keep you from falling through the curve. When you see it this way, the whole universe looks different. It's not a bunch of objects being pulled by invisible ghostly hands. It's a dynamic, wobbling, curving landscape. Even light follows these curves. When a ray of light from a distant star passes near the sun, it doesn't go straight, it bends. Not because the sun pulls on the light doesn't even have mass in the traditional sense, but because the straightest path through the space near the sun is a curve. We've measured this. During an eclipse in 1919, they saw the stars move. It was the moment we realized Newton's force was just a very good approximation of a much deeper geometric truth. People get stuck on the why. Why does mass curve space? We don't know the why in the ultimate sense. Physics isn't about the why, it's about the how. It's about finding the rules of the game. If you can find a set of rules that predicts how the light will bend, and how the planets will move, and how the clocks will tick, and those rules are consistent and simple, then you've understood something fundamental. The rule here is that the universe is a four-dimensional manifold. That's a fancy word for a shape. We live in this shape, and the shape changes depending on what's inside it. It's like a conversation between the stuff and the space. Now, why does this matter? Is it just for astronomers? No, it's for anyone who wants to see the integrity of nature. When you see gravity as geometry, you stop seeing the world as a series of disconnected events. You see the unity. You see that the falling apple, the orbiting moon, and the ticking clock are all doing the exact same thing. They are navigating the ripples in the fabric of reality. I want you to think about the beauty of that. It's much more elegant than a force. A force is something you add on top of the world. Geometry is the world. It means the laws of physics are built into the very structure of where we are and when we are. There's no action at a distance that worried Newton so much. There's no magic signal traveling through the void. There's just the local shape of the space right where you are. When we study the atom, we find different rules, quantum mechanics, and trying to make those rules fit with this curved space idea is the big problem we're still working on. It's the great unfinished symphony. So next time you feel heavy, don't think of it as a tug of war with the earth. Think of it as your body trying to follow the most natural, straightest path it can through a universe that isn't flat. You're not being pulled, you're just trying to move, and the earth is getting in your way. The mystery isn't in the pull, the mystery is in the curve, and that curve is everywhere. It's in the room with you, it's between the stars, and it's what holds the whole grand mess together. Nature has a way of being much simpler and much more complicated than we imagine, all at the same time. The force of gravity is a perfect example. It's a simple word for a complex geometric reality. And if you can wrap your head around that, even just a little bit, you'll see a world that is far more interesting than the one you were taught in high school. You'll see a world that isn't just a place where things happen, but a world that is happening all by itself through its own shape and its own rhythm. That's the real kick. That's the fun of it. I've always found it amazing that we can even talk about these things. How we are, these little collections of atoms, standing on a rock, looking out into the dark, and we can figure out that the space between us and the stars is curved. It doesn't help us find food, and it doesn't help us run faster. But we do it because we're curious. And nature rewards that curiosity by revealing these deep, hidden patterns. So gravity isn't a force. It's the way the universe breathes. It's the way it holds its shape. And once you see that, you can't go back to the old way. You're stuck with the truth. And the truth is always much more exciting than the simple stories we tell ourselves to feel comfortable. It's the pleasure of finding things out. And today, we found out that the ground isn't just under your feet. It's part of a curve that stretches out to the ends of time. If we want to understand the way the world is put together, we have to look at the details. We have to look at how light behaves, how time behaves, and how matter behaves. And when we look at them all together, they tell us a story of a curved universe. It's a story that doesn't need forces to explain it. It just needs a little bit of geometry and a lot of imagination. That's the beauty of physics. You take something as common as an object falling, and you follow the logic until you realize the very nature of space and time is different than you thought. It's a complete revolution in your head, and it all starts by asking, what if there is no force? Once you ask that, the whole universe opens up.